It's Paul Bamberg here with a Math156 script designed to show you how you can apply bootstrapping techniques to real-world data. I strongly encourage you, as usual, to read the relevant sections in the textbook, and my first topic is example 5.3 in the text involving concentrations of arsenic in well water in Bangladesh. After reading this, if I ever tour Bangladesh, I am going to drink bottled water. Thank you. So we've all got this in a file. Read it in, and you can see this data frame has 3 columns giving concentrations of arsenic, chlorine, and cobalt in the water. We're going to concern ourselves with the arsenic distribution. Let's have a quick look at the histogram. It looks a little bit like a chi-squared distribution, but it's a real-world distribution. It's certainly by no means normal, and it's got a rather large skewness. A good way of showing how seriously it fails to be normal is to compare the quantiles with those for the normal distribution by using QQ norm, and you can see we don't get anything even remotely resembling a straight line. How many samples have we got? We've got 271 samples, and with this large a sample, the central limit theorem still doesn't give us a good approximation. So let's bootstrap the data. We will do 10,000 bootstrap samples, store them in the numeric array arsenic.mean, and so 10,000 times what we will do is draw 271 samples with replacement from this sample of 271. That is, we will reuse some of the measurements, we will ignore others of the measurements, and we will thereby create a bootstrap distribution which we can plot. And this looks considerably more reasonable, doesn't it? It's a histogram, but it's certainly not symmetric. It has captured the fact that the original distribution was seriously skewed to the right. If we look at the normal distribution with the same mean and the same variance, we see we don't have a perfect matchup. In particular, on the right-hand side, the actual data are significantly above the normal density function. On the left-hand side, they're significantly below it. That's what the skewness is telling us. And if we look at QQ norm and actually draw a QQ line, we can see that out on the fringes we have a distribution that is significantly different from a normal distribution. Now, the lazy way of getting confidence intervals is you assume that all distributions are normal. Go 1.96 standard deviations from the mean on either side. And if we do that, we can look at the normal distribution and plot the relevant lines. 2.5% of the density function is below the red line, 2.5% is above the blue line. If, on the other hand, we look at our bootstrap distribution from the arsenic concentrations, we find that we're only below the red line value 1.5% of the time. We're above the blue line value 3.4% of the time, and we have the usual problem of a confidence interval with the property that we're wrong on one end significantly more frequently than we're wrong on the other end. This is an attempt to replicate the bootstrap distribution of the means from the textbook. Of course, mine won't agree perfectly with theirs because we each drew a different random sample. Nonetheless, we can look at this and show the low and high numbers from the assumption that it's a normal distribution. And you can see by looking at that that we're above the blue line more frequently than we're below the red line. We can use the bootstrap distribution to get what's called a 95% Bootstrap percentile confidence interval. And this is going to give a different result from the one I showed you in the immediately preceding script. This is a technique whose main merit is that it's extremely simple. That is, we just take this bootstrap distribution, arsenic.mean, and ask for the 2.5% and 97.5% quantiles. And we plot those as dotted lines. So they capture a so-called bootstrap percentile confidence interval with 2.5% on either side. And if you look, you'll see it does now appear that the fraction of the time we're above the blue dotted line equals the fraction of the time we're below the red dotted line. Here's another way of doing this. This is the approach I used in the last script, using a basic bootstrap confidence interval, so-called. And in this case, when we tried this with a known population, when we knew we were drawing samples from a gamma distribution, it gave a pretty good confidence interval. So we're computing from the lower quantile how much to add on to the sample mean. From the upper quantile, we're computing how much to subtract. And when we do that, we get a couple of other lines, which I am now going to plot. Those are the dotted lines. And you'll notice that both the basic and percentile bootstrap confidence intervals disagree with the naive approach using the normal distribution, but they disagree in opposite ways. I continue to think that the percentile confidence interval just makes things worse. I've exchanged several emails with one of our authors, Tim Hesterberg, about this, and I finally have decided that I don't understand his arguments that no, the percentile confidence interval really corrects for something else. So you can do one or the other. Anyone will give you a confidence interval where you've got a 95% style of catching the mean. I personally think the basic confidence interval gives you symmetry with respect to errors on the two sides. Okay. Now, let's suppose we're trying to compare two samples. This is example 5.4 from the textbook, and you might want to read the relevant section before continuing. You have read the relevant section? Fine. Let's continue. The great thing about videos is you can stop them and do some reading. So this is data about commercials on TV, and in particular, when you look at this, you get, for basic cable and extended cable, the number of minutes of commercials within a 30-minute segment. And just looking at this, you can say, ha, I suspected it. You get stuck with more commercials on basic cable than on extended cable. So let's look at the difference in the means. And let's do this for 10,000 bootstrap samples, because here's the problem we've got. We can average together these basic times. We can average together the extended times. We can take the difference, but we've got no firm basis for saying whether this difference is statistically significant or not. And in accordance with our general resampling philosophy, what we're going to do is get a collection of 10,000 random samples with which we can compare the actual data. So we do this, 10,000 bootstrap samples. We will sample from the basic with replacement, sample from the extended with replacement, take the difference, and plot a histogram of the result. Now from that we can extract a 95% confidence interval just by asking for the quantiles of this distribution, and we say 95% of the time the true mean in the difference will lie in between 0.9 and 3.8, And since those are both positive quantities, we're fairly sure that the true mean really is a positive number, that there are more commercials on basic cable than on extended cable. Now, when you're bootstrapping, you don't have to confine yourself to differences. Here's another of the book's favorite data sets, the data for repair times for telephones. And on reading the book, I get the impression that Tim Hesterberg probably appeared as an expert witness in a court case involving Verizon on this issue. So what we've got from this Verizon data is repair times for Verizon customers and repair times for competitors' customers. CLEC begins with competitors. I think that's how you know it's the competitor one, but it's a much smaller group also. And a reasonable statistic here is the ratio of repair times. On the average, it takes twice as long for a competitor's customer to get the repairs done. A warning about these ratios. A ratio like this is a biased statistic, by which I mean that the mean of the sample does not equal the ratio of the means, and this is a phenomenon for which you really ought to correct. Okay, let's do our bootstrapping. So we'll set up two numeric arrays to hold our bootstrap sample. We will do 1,664 samples from the Verizon customers. We will do 23 samples from the competitors' customers. And the tradition here, though I don't think it's an absolute requirement, is when you're doing bootstrapping, the number of samples you draw with replacement is equal to the number of samples that you already have on hand. Compute the mean of one, compute the mean of the other, and then take the ratio. So this is like saying 10,000 times we're going to get some repair times for Verizon customers, repair times for competitors' customers, take the means of those samples, and then average them, and we can see where the actual data fits into that. Well, here's a histogram of the ratio. Here is the mean ratio plotted on that. The mean time taken for Verizon customers is about half the time for competitors' customers. And here, for comparison, is the mean time for Verizon over mean time for competitors. That's plotted in blue. It's slightly different. That's an indication of the bias that results just from using ratios as a statistic. Let's compare this with a normal distribution. If we look at it, we see QQ norm doesn't give us anything remotely resembling a straight line. When we compare it with a straight line, we see compared with a normal distribution, this is seriously skewed. Now, in this case, in addition to computing the quantiles for 2.5% and 97.5%, I'm going to compute the bias. When I talk about the bias, what I mean is the mean of the time ratio compared with the ratio of the means. That's 0.02. Is that big? Is it small? Well, a reasonable thing with which to compare it is the standard deviation we get from our bootstrap distribution, which is about 6 times larger. So this bias is not 0, but it is not wildly significant. Figure 517 in the textbook is a nice scatter plot of these data. Let me show you how to create that. First, you create a blank plot, and you label the x and y axes. And then on that, you plot as a vertical line the mean repair time for the competitors' customers, and as a horizontal line, the much smaller mean repair time for the Verizon customers. Now we've got our bootstrap distribution of time ratios, so we can plot as sloping lines the 2.5% quantile and the 97.5% quantile, and we say 95% of the actual data that we get fall in between those two lines. We can actually plot the 50% quantile too. What do you know? That green line doesn't go through the intersection of the two red lines. That's just an indication that ratios are a bias statistic. So what's our bootstrap confidence interval? It's between the blue lines. We can say we're not sure that we've got the actual true ratio of repair times, but on the basis of our bootstrap, we say it has a 95% chance of lying in between those sloping blue lines. And since both sloping blue lines show that it takes less time for a Verizon customer to get a repair than it takes for a competitor's customer, that's a fairly convincing argument that the smaller repair times for the Verizon customers are a significant statistic.